The USS Raleigh was moored at berth F-12 in Pearl Harbor on the morning of December the 7th, 1941. In the first attack wave, one aerial torpedo ran ahead of her bow and struck Ford Island without exploding. A second torpedo found its mark moments later, detonating against Raleigh's portside amidships. The blast tore the ship open below the waterline and drove her into a dangerous list to port. In those first chaotic minutes, a capsize looked frighteningly possible, and only rapid damage control and outside assistance kept the light cruiser upright at her moorings. The torpedo detonated on Raleigh's portside amidships, about 13.5 feet below the waterline, just under the armor belt. Underwater, the blast and gas bubble have nowhere to vent the way they would in air. As the shock is driven straight into the nearest structure, the cruiser's submerged steel skin. The initial rupture tore plating at the impact point, but the larger danger was the shockwave radiating through frames, seams, and riveted joints, buckling structure well beyond a single patchable hole, and pushing metal past its design limits in an instant. That violent distortion created a lethal secondary problem: open seams and leaking riveted joints. Ships of this era relied on overlapping plates locked together by heavy rivets, and a torpedo shock can spring those rivets, deform the laps, and turn what should be tight seams into multiple pathways for flooding. Even if the main rupture is limited to the strike area, the surrounding structure can be left warped and leaking with watertight integrity compromised well beyond a single clean hole. And the result was rapid, hard-to-control flooding. Ship reports describe the torpedo hit flooding the number 2 fire room, while the number 1 fire room, then the steaming fire room, lost its fires as water and oil spread. Engineers fought to keep the inrush from reaching aft machinery and boiler spaces, knowing that once those compartments went, the fight to keep the cruiser afloat would be nearly over. Flooding was heavy and fast, measured in minutes, not hours. With flooding and weight shifting on the port side, the ship's balance margin collapsed and the list to port became alarming. Naval architecture can be unforgiving once stability is badly degraded, and on board Raleigh, the list to port was already alarming. Rolling completely over at her moorings would have trapped men inside a flooding steel hull and could have turned the cruiser into a total loss. Survival demanded an immediate and counterintuitive decision: counterflooding to bring the ship back toward an even keel. It is a terrifying order to execute on a damaged ship, but Raleigh's damage control organization moved fast, counterflooding promptly and in the proper sequence, while other hands fought flooding and prepared to jettison topside weight. Within about 15 minutes of the torpedo hit, those actions were underway, part of a wider, desperate effort to keep the cruiser from rolling over. By letting water into selected spaces on the starboard side, the crew created a counterweight that helped check the worst of the list. The immediate threat of a sudden roll was eased, but the ship was far from safe. Floodwater inside the hull could shift, and every change in angle threatened to turn stability into a swinging, unpredictable battle below decks. The crippled cruiser was now trapped in a terrifying mechanical pendulum, swinging unpredictably from an 11-degree port list to an 8-degree starboard roll. This was not the natural motion of a vessel yielding to ocean swells. This was the unmistakable signature of a dying hull. Naval engineers refer to this critical condition as a tender ship. The successful counterflooding executed in the immediate aftermath of the torpedo strike had stopped the initial plunge, but it had introduced a new, equally lethal physical reality to the lower decks of the warship. The massive volumes of ocean now trapped inside the engineering spaces and voids were not locked solidly in place. Because the internal bulkheads and structural seams were severely ruptured, the floodwater remained entirely loose, creating a deadly hydrostatic phenomenon known as the free surface effect. When a heavily flooded ship shifts even slightly to one side, thousands of tons of internal water rush laterally across the full width of the beam. This violently shifting liquid mass constantly alters the physical balance of the vessel. The water always seeks the lowest point, forcefully dragging the ship further into the roll. In a stable, undamaged warship, the center of gravity stays low, and the righting force brings the ship back toward vertical whenever she rolls. That natural righting margin is tied to metacentric height, and it can be badly reduced by flooding and by the free surface effect. Inside Raleigh, that loose water kept migrating across the beam, shaving away what little stability remained. Each shift robbed her of righting force and threatened to drive the roll farther with every oscillation. As damage control fought the hidden stability crisis below decks, the enemy struck again from above. Shortly after 0900, a glide bombing attack came in, and one armor-piercing bomb struck on the port quarter. This was not a simple blast meant to shred topside plating. It was a hard-driving projectile intended to punch deep through steel and do its worst work below. The falling bomb struck the number 7 3-inch ready ammunition box. A glancing blow then drove on through the carpenter shop and down through an oil tank. It pierced the ship's skin on the port quarter below the waterline and still did not detonate inside the hull. The track of that projectile carved a localized disaster through compartments and structure, but the ship had avoided the single outcome that would have made damage control impossible. More critically, the bomb's path passed very close, about 10 feet, to 2 large tanks holding 3,000 gallons of high-test aviation gasoline. A detonation inboard at that proximity could have turned the stern into an inferno and ended the fight to save the ship. Instead, after piercing out below the waterline, the bomb detonated on the bottom of the harbor about 50 feet from Raleigh. However, the bomb's passage still opened a fresh breach below the waterline, multiplying the flooding points and worsening the free surface sloshing inside the hull. With the last margin of righting moment collapsing, the problem became brutally simple. Keep the ship from rolling over long enough for salvage to work. Captain Simons ordered immediate engineering triage, jettisoned heavy topside weapons and gear into the harbor to drive the ship's center of gravity down and buy back a fighting chance of stability. In naval architecture, stability depends heavily on how high the ship carries its mass. Heavy gear high above the waterline raises the center of gravity, and when a flooded ship starts to heel, that elevated weight acts like a lever that pulls the roll deeper. Stripping dense equipment off the deck and superstructure lowers the center of gravity and restores some righting margin, sometimes the only margin a damaged hull has left. This operational logic is completely straightforward when a ship sits safely in a dry dock. However, executing a massive weight reduction during an active combat scenario presents an entirely different physical reality. A modern warship is designed specifically to retain its massive equipment during heavy seas. Furthermore, the massive underwater damage had completely severed the electrical power flowing to the heavy deck cranes. The mechanical advantage normally used to lift and maneuver heavy armament was permanently gone. The crew had to rely exclusively on pure human muscle power to dismantle, drag, and eject the enormous weight. They had to achieve this while standing on a deck that was actively slanting toward the water. The mandate was brutal: strip away as much topside weight as human hands could move, later estimated at about 60 tons, without ship's power. Men swarmed the decks to disconnect and shove heavy gear overboard. Both anchors were let go, and both observation seaplanes were hoisted out by hand, set in the water, and sent taxiing to Ford Island to report for duty. Crews also jettisoned the aircraft catapults, torpedo tubes, and the steel cargo boom, and even pushed the torpedoes themselves overboard by hand, minus their warheads, to be beached at Ford Island for recovery. The jettison steadied the motion and bought time, but it did not restore the buoyant volume the hull had lost below the waterline. Raleigh could be kept from rolling over. It's not made whole, meaning salvage still had to find a way to add stability from outside the ship. Securing artificial stability required trapping an immense volume of exterior buoyancy directly beneath the slanting steel of the damaged hull. The violent reduction of internal mass had successfully halted the immediate capsize, but the vessel still critically lacked the fundamental mechanical leverage required to stay permanently upright. The remaining engineering solution required radically altering the exterior footprint of the warship. If the cruiser could no longer rely on its own internal weight distribution to fight the ocean, it had to borrow external buoyancy from another vessel entirely. The strategy was to create a massive artificial outrigger, external buoyancy placed far outboard to resist the list. A reinforced lighter barge carrying large salvage pontoons was brought tight alongside Raleigh's port quarter, but proximity alone would not stop a roll. The two hulls had to be made a single mechanical unit, with the barge rigidly pinned under the cruiser's overhanging curve, so its buoyancy could physically oppose the downward force of the list. Achieving that rigid brace required hard, methodical rigging. Heavy steel hawsers were led under the ship and secured to the lighter and its salvage pontoons so they could be positioned and held as an outrigger on Raleigh's port quarter. Once in place, extra lines to the keys helped keep the cruiser from rolling further while pumps, shoring, and damage control fought to regain stability. Once the steel cables were successfully positioned beneath the ship, they were hauled violently tight using heavy mechanical winches. This extreme tension forcefully dragged the barge inward, wedging it tightly against the outer steel plating of the cruiser. The rigid steel hawsers effectively locked the barge into a fixed geometric position relative to the main hull. The artificial outrigger was now formally engaged. The physical interaction between the two vessels instantly created a powerful external righting moment. Because the barge was tightly lashed beneath the overhanging list of the warship, any further attempt by the cruiser to roll to port directly drove the pontoon barge deeper into the ocean. Water is incredibly dense and aggressively resists displacement as the downward force of the listing cruiser pushed against the barge, and the sealed buoyancy of the pontoons generated a massive upward counterforce. The deeper the cruiser tried to push the outrigger down, the harder the ocean pushed the outrigger back up against the warship. With the barge locked under her portside overhang, its pontoons generated an external righting moment that the flooded hull could no longer produce. The hawsers took the load and held Raleigh upright long enough for pumps and shoring to work, but the rigging could not seal warped plating and sprung seams, and the sea still had open paths into the ship. It sounds insane to add weight while a ship is fighting to stay afloat. But once Raleigh was braced and time had been bought, salvage shifted from raw stability to one ruthless objective: slow the sea. Standard doctrine talks about collision mats pulled across a clean breach. But Raleigh did not have a clean breach. The torpedo and the shock had left distorted plating and irregular openings that flexible mats could not reliably bite into. Water would find the gap, slip past the canvas, and keep pouring in. Repair parties went straight to work. Divers worked at the bomb damage on the port quarter, forcing buoyant material into the opening to cut the intake and steady the situation long enough for more durable measures. Inside the ship, carpenters and damage control teams built heavy shoring where they could, reinforcing weakened boundaries, so the flooding would not spread into spaces that would finish the cruiser. Then came the semi-permanent answer. By December 15, 1941, underwater cement patches were applied over openings in the hull, battlefield engineering that reduced leakage, hardened damaged edges, and finally gave salvage pumps a margin to work. With boundaries reinforced and the worst inrush slowed, pumping and dewatering could make real progress, stabilizing a ship that had seemed minutes from rolling over. By the early days of January 1942, Raleigh was no longer taking on water, but the concrete repairs were never meant to be permanent, and the next phase demanded moving the battered cruiser into a repair dock where the hull could be rebuilt. Moving a severely traumatized hull through an active harbor is an inherently dangerous operation. The ship had successfully survived the static loads while completely tied down to her berth, but moving her meant introducing dangerous dynamic forces. The steel hull naturally had to flex and bend as heavy tugboats applied immense pushing and pulling forces to the bow and stern. Furthermore, the massive dead weight of the internal concrete patches added severe localized stress directly to the highly weakened internal framing. The entire structural envelope was highly compromised, meaning the transit required extreme navigational caution and absolutely precise speed control to avoid snapping the weakened keel. In early January 1942, the cruiser was carefully guided into dry dock number 1 at the Pearl Harbor Navy Yard. Entering a dry dock is a mathematically critical evolution for any healthy ship, but for a heavily damaged vessel, it becomes a perilous balancing act. The massive steel caisson gates closed firmly behind the stern, locking out the sea, and the pumps began draining the dock so the ship could settle onto her blocks. As the water level slowly dropped inside the massive chamber, the true exterior extent of the violent structural deformation was finally exposed to the open air. The ship slowly settled downward until its keel made firm contact with an array of heavy wooden docking blocks. These massive timber blocks had to be precisely arranged by shipyard divers beforehand to successfully support the massive abnormal loads created by the missing hull sections and the heavy temporary stone patches. The dockmasters had to ensure that the enormous weight of the cruiser did not simply crush the remaining intact framing, as the buoyant force of the water was gradually removed. When the dry dock was finally completely drained, as the sheer scale of the localized crush zone became fully visible to the shipyard engineers, the massive 50-foot-long indentation and the thousands of sheared hull rivets stood as silent testament to the extreme violence of the torpedo shockwave. The sight of the warship resting securely on the heavy dry dock blocks served as the absolute physical validation of the emergency damage control teams. Their extreme field engineering triage had worked perfectly. The men had successfully bridged the terrifying gap between a lethal combat environment and the permanent safety of a heavy industrial repair facility. Inside the dry dock, the slow process of permanent resurrection began. The heavy temporary structural stone was carefully chipped away and removed from the lower engineering spaces. Shipyard workers brought in heavy cutting torches to entirely slice out the violently deformed steel framing and the ruptured exterior hull plating. Massive sheets of fresh, heavy steel were carefully shaped and welded directly into the enormous portside void, permanently restoring the true watertight structural boundary of the warship. The heavy offensive weapons and essential operational equipment that had been desperately stripped away during the crisis were methodically replaced and perfectly rebalanced. The internal layout was fully restored to its original factory geometry. The immense effort expended to drag the ship back from the brink of a complete geometric capsize proved entirely justified. On February 21, 1942, the USS Raleigh departed Pearl Harbor for the Mare Island Navy Yard in California for additional repairs and upgrades. After overhaul, she returned to operational service, clearing San Francisco Bay on July 23, 1942, to begin convoy escort duty.